Student, in today's lecture we will be discussing numerical on design of slab. So we have taken an example here. Let's start. So the question is, a simply supported slab of a corridor of a hospital building has a clear span of 2.5 meter and it is supported on the beams 230 mm width. Design the slab if the beam is carrying a live load of 5 kilonewton per meter square. We have to use M20 concrete and HYHD FE 415 bars. So before proceeding to the design step, we will write down the given data. So first of all, for solving this question, we have to calculate the depth, overall depth and the effective depth. So we have assumed overall depth of 120 mm. So this assumption is taken from the ratio of L by D. L by D ratio for simply supported is 25. L given is 2.5 meters, so it becomes 2500 mm, and now D becomes L by 25 and L is 2500 divided by 25 becomes 100 mm. So the effective depth is 100 mm, but we are assuming a cover of 20 mm. So as we already discussed in the last lecture, that the cover provided for slab is minimum of 15 mm. So for factor safety we have taken it as 20 mm. So then we have to calculate the effective span, that is L. So there are two conditions in slab for calculating the effective span. First is the center to center spacing between the supports. So the clear span is 2.5 and the width of supports is 230 mm. So we have taken in meters, so it becomes 0.23. By adding this we get 2.73 meter. Second criteria for effective span is clear span plus effective depth. So clear span is again 2.5 meter, effective depth we have taken as 100 mm, so it becomes 0.1 meter, so it becomes 2.6 meter. Okay, so now we have to proceed for calculating the design loads, because the load given is W. So for calculating the design load, that is WU, and factored moment MU and shear force, we have to calculate this. So as we all know that the slab is designed for 1 meter width, so first of all we will calculate the self weight of slab. It becomes 0.12 into 1 into 25. Here 25 is the unit weight of RCC, which is 25 kilonewton per meter cube or 2500 kg per meter cube. So we will take in kilonewton, so it becomes 25 kilonewton per meter cube. Live load as given in the question, it is 5 kilonewton per meter square. So live load is 5 kilonewton per meter square, hence the total load, that is W, it becomes self weight plus live load. So 5 plus 3 becomes 8 kilonewton per meter square, but this load is the general load. So for designing we have to take it as a design load. So WU is denoted as design load. So WU becomes W into 1.5. Here 1.5 is the load factor, so 8 into 1.5 becomes 12 kilonewton per meter square. So the design of slab will be done for the total load or factored load of 12 kilonewton per meter square. Now we have to calculate the factored moment. So factored moment, as you all know that for UDL it is mu equals to WUL square by 8. So by solving this we get mu equal to 10.14 kilonewton meter, or if we convert it into Newton per mm, it becomes 10.14 into 10 power 6 Newton mm. Again we will calculate factored shear force. So factored shear force again for UDL it is W L by 2. So here W is WU, we are taking design load, so it becomes 15 kilonewton or 15,000 Newton, where L is the clear span. Now we will calculate the effective depth for which the slab will work. So here the grade of steel is given as HYHD bar and it is FE 415. So from the table of IS code we can easily calculate XU max. Here XU max is the critical depth of neutral axis in case of limit state method. So XU max by D is 0.48. So here RU is the design constant. We have also termed it as QU, so it can be written as QU or RU. So it becomes 0.36 FCK XU max by D multiplied by 1.42 1 minus 0.42 XU max by D. So here this constant become 2.76. PA we have already taken as unit in meter, so it becomes 1000 mm. So here depth required, by putting this in the formula, depth required formula is under root mu upon RB. So by solving this we get 60 mm. So hence 60 mm is less than 100 mm. So the depth required is come out to be less than the depth we have actually taken. So hence the design is okay. If this case has become opposite, then we have to redesign. We have to consider the higher value. So here depth required is less than the depth assumed, so hence it is okay. So hence we will adopt 120 mm as overall depth and small d effective depth is 100 mm. Here extra 20 mm is the cover provided to the slab. So D is greater than D required, hence the section is under reinforced. So we can easily design under reinforced section. So we will proceed further. So now we will calculate the area of tension steel or tensile steel, which is denoted by AST. So here AST again is calculated by using the formula of moment of resistance. So MU equals to 0.87 Fi AST, D multiplied by 1 minus AST Fi whole upon FCK BD. So this whole term you have seen in the IS code page number 96. You can easily see here. So by putting the values of the known, so here we know the value of moment of resistance, so it is 10.14 into 10 power 6. AST we have to calculate, so all the other terms are known. So here becomes an quadratic equation. We will solve it using the calculator and the AST becomes 300 mm square. So we have find out the total area of tensile steel which will be used in the design of slab. So in the case of slab we will use 8 mm diameter bar. So we have to calculate the area of one bar, that is A5. So A5 becomes pi by 4 8 square. It becomes 50.3 mm square. Now we have to calculate the spacing of bars. So spacing, the formula we have known that 1000 into A5, where A5 is the area of one 8 mm bar and AST is the total area of tensile steel. So by solving it we get 160 mm. So we have taken round off figure, so we have take 160 mm. So for calculating the spacing we have to check the three criteria. One is the spacing which we have got from the formula. Second is 3 times the effective depth, so 3D, so it becomes 3 into 100 300 mm, and third is 300 mm. So whichever is the minimum we will provide that particular spacing. Okay, so AST provided can be easily calculated from there also. So AST provided becomes 1000 into 50.3 upon 160. So we have again used the formula of spacing. Now we have calculated the area of steel as per the spacing which we have calculated. So AST becomes 314 mm square. So now moving forward, so as per the IS code, the minimum area of reinforcement, now we have to calculate the minimum area of reinforcement. So for HYHD bars, we've already discussed that for HYHD bar the minimum area AST minimum is equal to 0.12 into BD divided by 100, or we can say it 0.12% of the total area of cross section. So it becomes 144 mm square, which is less than 300 mm square. So hence it is okay, the design is okay, we can proceed further. So therefore we will provide 8 mm dia bars at the rate 160 mm center to center in shorter span. So this is a slab, so in shorter span the bars will be provided 8 mm bars at the rate 160 mm center to center. So we have provided the number of bars as well as the spacing. So at the support we have to provide the shear reinforcement also, and as we know that the shear reinforcement provided in slab is in the form of bent up bar. So at the center of the support from the face of the support, we will bend the half of the bars. So half of the bars is bent up like alternate bars. So by bending half of the bars at 375 mm, so here 375 has come out because we have to bend up the bar at from L by 7 distance from the center of the support. So from solving this L by 7, it becomes 371. So again taking round of figure, which will be easy to be constructed. So we have taken 375 mm from center of the support, or this condition also implies, or from the face of the support. So we have, if we are calculating from the center of the supports, means these are the support where the slab will be rest. So these are the support. So if you are taking from here center of the support, then you will take as L by 7. But if you are taking from the face of the support, face means this, you will provide this formula. So you can take either of these. So AST provided at support will be half, because we are bending half of the total area. So 314 is the total area of steel provided, so it is become 314 by 2, so 157 mm square, so which is greater than 120 mm square. So hence it is okay. So we have to again do the checks. So for the other side, this is for the main reinforcement. Now as we know that this is a one-way slab, so we will provide a distribution steel along the longer span. So distribution steel, we have to calculate the area of distribution steel. So again, the minimum area for distribution steel in HYSD bar is 0.12 BD upon 100. So by solving this, we get 144 mm square. Again, we have to use some diameter for this bar. So for distribution bar, we have discussed that the area of the bar is 6 mm. We have to take minimum 6 mm. So we are taking the minimum value 6 mm bar. So again, A5 is the area of one bar. It becomes 28.3 mm square. So again we have to calculate the spacing for those. The spacing will be again 1000 into A5 upon AST. Here AST is the area of distribution steel, which we have calculated 144. So by solving this, we get SV as 196.5. So again we will take a round of figure. So SV becomes 190 mm. So we will provide 6 mm dia bar at the rate 190 mm center to center in longer direction. In case of only one-way slab, if we are designing two-way slab, then we will provide only the main reinforcement in both the directions. So again spacing will be checked. So for distribution bar, the spacing should be SV 5D or 450 mm, whichever is less from these three, we will take that value. So the lesser one is 190 mm. So these two values will be excluded. Now we have to check for shear, but as you know that the shear design in slab is always safe, but we have to check. So there is a check for shear. So again VU we will provide, it is the total shear force, it is 15,000 Newton. So we will calculate the nominal shear stress, that is tau V. It is calculated by the formula VU upon BD. So tau V comes out to be 0.15 Newton per mm square for M20 grade, and at support the AST will be, because the shear reinforcement is provided at the support only, so we will calculate the AST provided at support, which has already been calculated. It is 157 mm square. Percentage of steel we have to calculate, because this both value will be used for interpolation work or for the table. So PT becomes, percentage of steel becomes 0.15%. So as you all know that from the table of IS code 5.5, we will calculate tau C. Here tau C is the nominal shear stress for concrete. So for M20 and PT 0.15%, tau C comes out to be 0.28. We have already discussed this table in the shear reinforcement design, so you can take reference from there. Also for 120 mm depth, K is the modification factor, so K becomes 1.3. It is also can be seen from table 5.6. I have also shared this table, I will be showing you that. So this is the table. So it is a modification factor for tensile reinforcement. So percentage of tension reinforcement and modification factor can be calculated by using a percentage of tension reinforcement and Fs. Fs is the shear reinforcement, shear taken by the steel, so it can be calculated from 0.58 Fy into area of cross section of steel required upon area of cross section of steel provided. So here Fy is the grade of steel which you are using, so you can calculate from this table. So whatever value of Fs come, we will join the percentage of tensile reinforcement and the Fs value, and we will easily calculate the modification factor. So here I have already taken those values. For 120 mm that Ka becomes 1.3 and tau c for slab can be calculated by K into tau c. So we have calculated it 0.36 Newton per mm square, which is greater than tau v, which we have already calculated above. Okay, so hence it is okay for design. This is the value of tau v. So the check for shear is always safe in the case of slab, because the area of slab is very much greater than the area of beam. So this shear reinforcement is always provided as a bent up bar. Minimum reinforcement is provided. Now we have to check for deflection. Deflection means the slab should not deflect from longer or shorter span. So here for check for deflection, we have formula percent of steel. We have to again calculate percentage of steel. It becomes 0.31. We have already calculated it above. Fs you all know that Fs is the stress in the tensile steel. So the formula here, as you have seen from that graph also, it becomes 0.58 Fy multiplied by AST required upon AST provided. So we have 0.58. Fy is the grade of steel used, so we are using Fe 415, so it becomes 415. AST required is 300, AST provided is 314. So by solving this we get value of 230 Newton per mm square. So it is the shear taken by the steel reinforcement. So for PT percentage 0.31%, Fs is 230 Newton. For Fs 190, PT again is 0.31. So modification factor KT is 1.89, and for Fs 240, PT for same percentage of steel, KT is modification factor is 1.47. So I have mentioned all these three values for different stress values of steel. So it can be calculated from the table also, but for your reference I have mentioned it here. So for Fs 230, because in the question the Fs has come out to be 230 Newton square, so KT becomes, this is the formula for interpolation. I will send you this formula in your groups. So KT, by using the interpolation formula for 230, KT comes out to be 1.55. So L by D is the deflection control. So L by D maximum, deflection maximum becomes 20 into KT. It is from the formula itself of IS code. You can refer IS code for this. So KTS comes out to be 1.55. So L by D maximum deflection is 31. L by D provided is 2600 upon 100. So it becomes 26. L by D is the L clear span and D is the effective depth. So clear span provided is 22.6, so it becomes 2600 mm. D is 100 mm, so it becomes 26. So as L by D maximum is greater than L by D provided, hence it is okay. If the case have become opposite, then we have to again modify the dimensions. So here the check for deflection is again okay. So L by D maximum is greater than L by D provided. So here we have drawn the reinforcement detail for slab. So it comes out to be 230 mm is the width of supports, 260 mm is the length from the face of the support from which the bent up bars will be provided, and 250 mm is the from the corner the bent up bars. 6 mm is the development bars or the distribution steel which is using in the one-way slab. 8 mm is the main bar or the transverse reinforcement. 2.5 is the clear span of the slab, and 120 mm is the depth for those slab. So thank you so much for today.